This isn't the video I originally thought I was making. I was looking at how a swing works. I mean, I get that when you stand on a swing, you're heightening and then lowering your body, which changes the centre of mass. And I get that when you're sitting, there's also this transfer of angular momentum, which is from your back and your legs. So I was experimenting with this mechanical idea, and we'll come back to that later in the video. But the more I was putting weights on, I was thinking, is this really true that the mass that you put on the end of the pendulum has no effect on the time it takes to swing? And I guess that's one of the things this channel is about. Does the theory actually hold out on something that you can make yourself? And what can you learn from it? So 1602, Galileo, who I hope then looked a bit younger than he does in this picture, looked at a swinging lamp and later worked out that the time taken for each swing is independent of the weight hanging from the pendulum. So this is my pendulum. The geared wheel at the bottom of the pendulum we'll use later on to introduce rotation, but at the moment the wheel's just fixed onto the shaft with a bit of sellotape, you know, real high-tech stuff. So this one has no weight at all. This one has a small 12.7 steel ball, and this one has 25.4mm steel ball. Okay, I've got this first one lined up, let's let it go. Did you miss it? Yeah, I'm gonna have to slow this all down. Let's start again. I filmed this at 30 frames per second, and the timecode generator is set to thousandths of a second. So one frame of this video will last for 33 1/3 thousandths of a second, or milliseconds. It ignores the third, so you'll just see it going up in increments of 33. So the first pendulum is 0.966. And then the second pendulum coming in is 0.966. Wow. And then the third one with the heavier weight is 0.9601. Okay. Well, being out by 33 milliseconds is really not bad, and to be fair, the way I've sellotaped that steel ball to the centre of the pendulum, yeah, it's dropped a little bit there, isn't it? Okay, let's wind this forward and redo the experiment. You can see that the amplitude, which is the distance that the pendulum is swinging, is now considerably down. Okay, here we go. 0.966. 0.966. And 1 second. That is awesome. So it's right, the time it takes for a pendulum to swing is completely independent of the mass. The only thing that is important is the position of the mass, which basically means what the length of the pendulum is. And the formula to work out the time of a swinging pendulum has no mass in it. It's just the length of the pendulum, which in our case was 240mm, divided by gravity. And would you believe it? 0.983 milliseconds, right in the middle of our two results. And there's a nice relaxing pendulum. Okay, I'll release these again. After one swing, all three pendulums have travelled roughly the same distance. But if we let the swing continue for a bit longer, you can see that the pendulum with the heaviest weight is reaching higher than the lighter ones, and the heavier pendulum is definitely moving faster. And that makes sense, because if time isn't changing, then speed and distance must be changing. And the heavier pendulum took more effort to lift up before I let it go, so it takes it longer to get rid of that stored energy, which is why it's the last one to stop. Okay, I think I'm happy with that now, but what I started looking at was how someone on a swing puts energy into the swing. And that's a combination of the changing position of the mass, which we've just seen effectively changes the length of the swing, but it's mainly due to the transfer of angular momentum due to the swinging of your legs and your back. So I want to make a swing, a pendulum, that has a mass and also transfers that angular momentum. So that's what the gear's for. Okay, here it is assembled, and this bar is basically just to keep the gear away from the edge of the pendulum. I'm just going to print out a few more holders, and they're going to be able to hold the steel balls in different positions. I know that the friction on this is going to be considerable, but I want to see what effect a rotating weight has on the time period of the pendulum, and the friction should be the same for each of the experiments, so let's just see what happens. So this is going to be our control. The first pendulum has no weights on it, the second one has one weight on each side, and the third one has 3 weights on each side. Okay, if you've stuck with me so far, thank you, and you know how we're going to do this next. So the timings are different from our first experiment, but I guess we could expect that because we have added in friction. So I'll move the film on again, and then let's take another timing. Yep, there it is, exactly the same readings as we had earlier. So again, confirming that the mass makes no difference in this setup. So what about if the weight is unequally distributed? What effect does that have on the timing of the pendulum? One weight, 2 weights and 3 weights, but positioned on only one side of the wheel. Right, let's record these timings and then move it on again. Ah, 966 again. 933 and 900. Okay, that's the first time we've seen a change in timing. That's a change of 66 milliseconds and 100 milliseconds. Is that significant? Does the formula for time no longer apply? When you're on a swing, you're pumping your legs and moving the pendulum with your body, which is putting energy in. So where's the energy coming from on the wheel? So is that what is happening with the gear? So do we have the energy of the pendulum being transferred to angular momentum by the wheel, and then that energy transferred back to the pendulum through the gearing? I'm not going to speculate why that's happening, so I'm going to leave it there, but I would love to hear your comments on it. So back to my little robot friend on the end of the pendulum swing. I'm putting energy in by controlling 2 servos that are moving the weights back and forward. For weights, I mean a couple of hinges, but it'll do for the moment. And you can see from the white arrows that I've put on there that the swing is getting wider as I'm putting energy in. The question is, How much energy do I need to put in compared with how much energy you could tap out from the swing? I mean, let's be clear, we're not talking about perpetual motion here, but is it an efficient system? Well, thanks for sticking with me on this one, and if it's inspired someone to have a go at making something like this, that's brilliant. Thanks for watching, and I think you'll enjoy these videos coming up. See you on the next one.